doing a hypothesis test and doing a confidence interval with proportions. So everything we did, conditions and everything, dealt with proportions because that was categorical data. Now we're going to be talking about means. And there's a few different characteristics and a few different things that have to happen when we do problems with means. And so that's what we're going to talk about today. All right. First of all, if we were to do our hypothesis test and confidence intervals involving a mean, and then they give us a known population standard deviation. Okay, so you need to make note that if it's a sigma, it's the population standard deviation. Okay? And that would be great. That would enable us to calculate the standard deviation for the sampling distribution, and we would do this formula that we have done in the past. You remember that? Standard deviation over the square root of n is that standard deviation of the sampling distribution. Okay. However, what is most generally the case in real life, you typically do not have sigma. You most often do not have sigma given to you. So what we do is we have to use the S, standard deviation of the sample, which is the standard deviation of the sample. If I am using a standard deviation of a sample instead of the population, what do you think the qualities of it are going to be as far as variation of it? Do you think a standard deviation of a sample will be more or less varied than the population? More varied. Okay? So standard deviation of the sample is more varied than the standard deviation for the entire population. Because of that reason, they call this a standard error instead of standard deviation. It is not because there's a mistake. It is because it has more variation, so there's more ability to make mistakes because of the more variation. But it is just like the ones that we have already computed in Chapter 18, but it's using the standard deviation of the sample right there on top. Okay, so that's what we're dealing with when we do means. We have to address the fact that there is more variation because they don't have a standard deviation of the population. All right, so because a standard deviation of a sample fluctuates based on the sample size. Do you remember as n goes up, what happens to the standard deviation? So the standard deviation, which I'm writing as an S because it's going to be of samples, goes down. Okay? So because that standard deviation fluctuates based on how big your sample size is, then we have different distributions that are not necessarily normal, perfectly normal that uses the normal function. Okay? So we cannot use z-scores because z-scores are representative of a perfect normal curve. And we don't have that anymore since we don't have the standard deviation. We are going to learn about t-distributions instead of our normal distributions. They are very similar. Do you see these pictures here? They look a lot like the normal curve. They are just more varied. They are wider. They are spread out. They have more area in the tails. So, the t-distributions are unimodal. They are symmetric. They are bell-shaped, just like the normal, but they have fatter tails. They have more variation spread out. All right, so you can see the larger your n, you will be less varied. So then you will have a nice, narrower t-distribution. You'll start getting more closely clustered around the mean. But if I have a smaller n, it's going to be more varied and wider. So let's take a look at these right here. First, I want to address that these problems talk about this thing called degrees of freedom. And that's generally abbreviated DF. And basically that comes from sample size minus 1. And I'll tell you why we do that here shortly. But first, let's just look at these. My red curve here, which you have these drawn, you just don't have them in color. My red curve here has a degrees of freedom of 3. What does that mean that the sample size was actually? Correct, the sample size was 4. So this thing has quite a bit of variation. See how this red curve goes all the way out here? It's quite a bit more varied, has more area in the tails than the other curves. So when you have a smaller degrees of freedom and a smaller n, we have more area out here in these tails. More varied. Okay. Then look at the blue curve that I have here. And you have also, it's a degrees of freedom of 6. And n would then be 7. Okay. It is starting now to suck in and get more closely clustered around the mean. It is less varied. Okay. And so what happens is, look at the black curve. As your n goes to infinity, basically as your n reaches the population size, as n goes to the population, as n goes to population size, then you get the exact normal curve. So as your degrees of freedom get higher and higher and higher, you're getting closer to a real normal curve. Okay? So that's what's happened. So keep that in mind as we go through these. All right. So this is actually going to be just kind of a reiteration of what I've already said. We now have extra variation in our standard error because we use the sample standard deviation. Okay? We have to allow for this extra variation so that it does not mess up the margin of error. It does not also cause us to overestimate the p-value or get a smaller p-value than what it really is. The shape of these t-distributions change. They are no longer perfectly normal. They are similar, but more varied. So the facts about these t-distributions: bell-shaped, center around 0, symmetric about 0. Each one is different. So do you see there's like a whole collection? Every single n has a different curve. Every single n has its own t-distribution. Okay? And there's this guy named Gossett, and I actually will have a longer class period. I can tell you his story tomorrow. And he spent the time to compute every single one of those tables based on a different n. Okay? So, all right. As n gets greater, the t-distribution gets closer to the normal curve. The degrees of freedom is n minus 1. And the degrees of freedom are telling us which t-distribution will be used. So which particular curve will get looked at. All right, so turn the page. And I just want to kind of clarify, I want to explain to you why degrees of freedom is n minus 1. I just want to make sure you've got that understanding. Say that I use this curve for n. Well, what happens if, I get this p-value right here, and that's considered significant, and it causes me to reject or whatever, I need to just make sure that I am not overestimating. I want to give myself a little more buffer to make sure that I'm not being too accurate with the curve. So therefore, the curve that gets used is one that's a little bit more varied, the n minus 1. So that way, we will be sure to not overestimate our probability, or underestimate, however the case may be. Okay? So we're just going to use the next curve down, the n minus 1, which is a little bit wider and more varied than straight up using the curve based on our sample size, because we just want to be extra careful. So this ensures that you are using a wider, more varied t-distribution than the one that corresponds with your n. So this way, we are kind of playing it safe so that we do not overestimate and use the one for our exact n. So that's why degrees of freedom are n minus 1. It gives us a little more freedom in our estimates, in our conclusions. What? That's called degrees of freedom, and we use that. Then that means degrees of freedom is the name of the t-distribution that will be used. So if I say sample size is 8, and the t-distribution I use is degrees of freedom 7, so I use the t-distribution based off of 7. I'm going to show you that right now. So here we go. So let's talk about plugging that in, and we're going to talk about calculator use here. Okay, so in our inverse norm and our norm CDF, which are now going to be T-CDF and inverse T's. Okay, so here we go. For hypothesis tests, when we do our test, we are going to have a T-statistic or a T-score. No longer Z-scores, okay, because this isn't completely normal. This, of course, is because the distribution that our data falls into is not actually normal. So when we do our conditions, which we're going to talk about tomorrow, we will actually end with approximately normal model applies. See, these are now approximately normal model, not the exact normal model. Okay, so look here. X bar is your sample mean. Mu is the population mean. This is like z-score. When we did our z-scores, we used to do this. P hat minus the true p over that standard deviation of p1 minus p over n. But now we do x bar minus mu over the standard error. So we also, in our calculator, will use this, T-CDF instead of norm CDF. And look at what's happening. In the parentheses, you'll have the lower t. You know, we used to go calculate from a z to a z. Well, now we calculate from a t-score to a t-score. But here's what's different. You have an extra thing that has to be in the parentheses. It's the degrees of freedom. Because this tells the calculator which curve to calculate off of. Since you are not calculating off of the perfectly normal curve, this degrees of freedom tells the calculator which t-distribution to compute off of. Okay, so that's why we have to include that in our little parentheses. So, for confidence intervals, if we want to get a t-star, see, look here. It used to be our confidence intervals were p hat plus or minus our critical value times this. Okay, but here we have means, the sample mean plus or minus a t-score critical value. That's your critical value. And then here's the standard deviation for means. So the way you get a critical value is inverse t of one tail, inverse t of one tail, but then tell it which curve, comma, degrees of freedom. See? Tell it which curve. Inverse t of one tail, comma, degrees of freedom. So let's practice that in our calculator. Here we go. Now, if you have a TI-83, a TI-83, okay, does not have the inverse t ability. Okay? So you'll just have to look on with somebody. So a TI-83 calculator does not have the inverse t capability. There's one more it won't have this year, but we'll get to that later after spring break. Okay, so let's do this critical value. It comes from a sample of 15. That means n is 15 observations, with a probability of 0.025. So that's what's in your tail. Okay. So I want to find that t-score. I'm going to do inverse t of one tail, comma, degrees of freedom. Tell it which curve to look on. Which t curve should it look on? Degrees of freedom? 14. because degrees of freedom is n minus 1. So you find that, same place as before, second vars. Number 4 is inverse t, and you may not have this exactly, you might have just a parentheses that shows up, but I'll show you what goes on here. It's going to put it in parentheses. Okay, so if you don't have this particular operating system, you just have that 0.0525, 14, and then it calculates. It actually takes a little longer than your z-scores because it has to think. It has to locate that. I mean, if you were look at the time on that, it's actually a little longer in its processing time because it has to find the correct curve and then give you that score. So this t star is negative 2.14. All right, so let's do the next one. This next one says we have a simple random sample of 20, and we have a 99% confidence, which means if I have 99% confidence interval, what's in a tail? 0.005. Half of 1% is in a tail. So I'm going to be going inverse t of 1 tail, comma, what will my degrees of freedom be for a sample size of 20? 19. Okay, so plug that in.
Switch two ways to find it?
No, I was just like in the wrong place. Okay, so this critical value is negative 2.86. Okay. Now, please be aware that on the next two, you are actually told the degrees of freedom. They are not telling you the sample size. So you have to make a conscious effort to pay attention. Are they giving me n, or are they giving me the degrees of freedom? Okay, so that you know if you need to subtract 1 or not. So find this one really quickly. This one's going to be your inverse t of 0.05, comma 5, because it actually is that degrees of freedom. Then you get that one. I want to do the last one because it's the only one of these that actually comes out with a positive. The t-distribution for 21 degrees of freedom has a probability of 99% to the left of what critical value? So this is 99% is down here below this t-score. So how am I going to figure that one out? Inverse t of what's below it, comma, degrees of freedom. So I'm going to use what number? 21, because see this? It gives me degrees of freedom, not n. So in actuality, n is 22, by the way. The sample size is 22. So it's critical that you keep n and degrees of freedom straight. TCDF on a Phantom's model. Okay, which we're going to do here shortly. All right, questions? There we go. Okay, so that's straight up computation. I tell you what, I want to skip these top two right here for now and do them if we have time, because I want to go down here and do a Phantoms and a Panic, but it'll be a little shorter because our conditions have been met. So here we go. Example 1. Andre is a waiter in San Francisco.
So you don't have to write conditions anymore.
Correct. On this one, because it tells us they're met. The IRS is doing an audit on his tax return this year. In particular, the IRS wants to know the average amount Andre gets for a tip. So that's what the IRS is wanting to estimate. In an effort to satisfy the IRS, Andre took a random sample of 8 credit card receipts, so I'm thinking right now N is 8, each of which indicated his tip. The sample mean is 12.35. How do I notate that? Sample mean. X bar, 12.35. And the sample standard deviation is 2.25. That's your SX. All right. Assuming the distribution of tips is unimodal and symmetric, approximately normal, not purely normal, and that all conditions have been met, because we're going to talk about those tomorrow, find a 90% confidence interval for the population mean of tips received by Andre. All right, so for a panic model, but we don't have to do the A part of the panic model. What does P stand for to do in the panic model? No, it's population parameter. What is the population you are inferring to? I am inferring to the entire average. Do you see how I have a mu here, not an X bar? No X bar. This is the population. I'm trying to find the average. I'm trying to estimate an average of all of Andre's tips. And I'm going to make this estimate from just one sample of 8 tips. Okay, so you have to think, what are you going to make an inference about? The average of all of his tips. It's average of all of his tips. You'd put all the amounts together and then average. Okay? Now, A is the assumptions, which we're not going to do. N is the name of this. This is a 1 sample T interval for means. 1 sample T interval for means. See, because our past one had proportion in the thing, we didn't have to say 4 proportions. It said 1 proportion T interval. This one says 1 sample T interval for means. Okay? N is to name it. We just did. I is the interval itself. Okay. So do you remember that? Let me just kind of do the formula and then we'll go off of that. You don't have to write this part, but I'm just doing this to remind you. It's the statistic plus or minus the critical value times the standard deviation of that statistic, which is S of X over square root of N for right now. So the statistic in this case is the sample mean. So that's the X bar. It used to be last unit P hat. But now it's the X bar because it's about means. So let's put some numbers to this. So what number goes here? 12.35 plus or minus critical value. Let me put this in here, and then 2.25 over the square root of what? 8. Okay, now critical value. How are you going to do that? Inverse T of 1 tail, which would be 0.05. Degrees of freedom are 7. Okay, that ends up being the negative 1.89, but I just always put it in here as positive because this plus and minus accounts for the signs. All right. So this comes out to be like 10.85, I think, to 13.85. I think that's somewhere where it comes out to be. So I need to write this conclusion, and I didn't give myself very much room. So let me see if I can't squeeze it in here. I am 90% confident, because this is an interpretation of the interval, that the true what? Average of all of Andre's tips. The true average of all Andre's tips is between, I think it ended up being 10.85 to 13.85. I'm not positive on that, but I think that's what I remember somebody got last class period. Okay. Ta-da! All right. So, that's a panic model without the A, because we're going to talk about the assumptions tomorrow. They're really pretty much the same. I just want to, tweak some details, but we don't have time on that today. So let's do this phantoms model. This is test the claim, so that's a phantoms model, that the IRS makes Andre makes more than $10 per tip on average. Okay? So that means it's the same thing. Our mu is actually still the same thing. So let's go straight to the null hypothesis. The null hypothesis is going to be what? If you're going to college class, I guess you can slide out, but you might have to, get help on this or watch this. So the null hypothesis is that mu equals $10. People, it is crazy important. If you do not put mu here and you put x bar here, it's wrong. This is an inference about the population mu. Okay, what would the alternative be for this one? That mu is greater. They said more than. They say Andre makes more than $10. Okay, so there's P and H. A is going to be the assumptions and conditions, which are already met. N is a one sample t-test for means. Okay, so there's PHAN. Now we do the test statistic. The test statistic is your t-score. Let me go ahead and write the main formula. That's your sample mean minus the population mean, which is the claim, over this, oopsie, that's wrong. Standard error. Okay? So, when I do that and fill in the blanks, I got 235, 1235 minus 10 over this thing here, which, man, I don't remember. It's like 0.795 or something like that. Well, this comes from 225 over the square root of 8, which is 0.795. Okay, so when I do that, so 10 divided by 0.795, I get 2.96 as a z-score. Or, oopsie, it's not a z-score. What is it? It's a t-score. So if I am to find the p-value, I actually go t-CDF from 2.96 out to infinity, comma, what? Degrees of freedom, which they are 7. Okay? You see that? Okay, so your TCDF is found, and we haven't done one of those yet, but your TCDF is your second bars. Number 6 is TCDF, and I'm going from 2.96, comma, 99, and 7 degrees of freedom. And so it looks like that. Enter. So my p-value is 0.0106, I guess. 0.0106. And then we're going to make a decision now. So our p-value of 0.0106 is less than alpha at the standard 0.05. So what's our decision? We are going to reject the null. So since the p-value is less than alpha, I reject that the average of Andre's tips is $10. I have evidence that what? That the average of Andre's tips is actually greater than $10. I have evidence that the average of Andre's tips
Good morning, staff and students.
is
Would you please stand and
greater
raise your right hand over
than.
your hearts, please, and recite the Pledge of Allegiance with me.
Hey, you can do the rest. You can do your homework now.
United States of America, and to the republic for which it stands, one nation, under